In this video, I would like to discuss few very special examples that involves computation of orthogonal complement of the given subspace of the vector space V. Alright, I will show you a couple of different examples. Let me start with this example that is kind of ideal problem. Let W be a subspace of R4 generated by these two basis vector W1 equal to 1 2 1 4 and W2 equal to, let's say, 1 2 7 3. Okay, so suppose W is a subspace generated by these two vectors, meaning these two vectors are the basis for subspace W. Every element, every vector in W can be expressed as a linear combination of these two, in other words. What I want you guys to do is compute the basis for orthogonal complement of W. Alright, so compute W perp or compute basis for orthogonal complement of W. Okay, let's try to understand that how the idea of that big picture can help here. Okay, we know that row space is orthogonal to the null space and they both forms orthogonal pieces of Rn. So I would like to do something similar in here for R4. R4 is a vector space, this is a subspace in R4. Okay, so what I'm gonna do here is I will assume that let W, which is set of these two vectors W1 W2, be the row space of A. Alright, suppose this two vector forms a basis for the row space of A. All I have to do is, in order to find its orthogonal complement, I'll have to find out the basis for the null space. Okay, so let me write down this row space in terms of this basis vector W1 W2. These are two vectors sitting in the rows. Alright, 1 2 1 4 1 2 7 3. All I have to do is find out the null space of this matrix and I'm pretty much done. Find out the basis for the null space. Convert this matrix into one of those echelon form. Multiply row number 1 by -1, add it to the second row. I really end up getting 1 2 1 4, -1 plus 1 0, -2 plus 2 0, -1 plus 7, that is 6, and -4 plus 3, that's -1. Alright, looks like we have a pivot sitting in the first column and third column, meaning x2 is a free variable, x4 is a free variable. This is the leading variable, that one is the leading variable as well. My goal is very clear. I'm going to assign a parameter for free variables. So let's say let x2 be s, x4 be t, and let's solve the leading variable in terms of free variables. So I'm going to write down that second equation, 6x3 minus x4 equal to 0. This gives me 6x3 minus t equal to 0. Solve it for x3 in terms of t. Looks like t over 6 is what we get. Write down the first equation, x1 plus 2x2 plus x3 plus 4x4 equal to 0. I'm gonna plug the values of x2, x3 and x4, and I'll express x1 in terms of linear combination of s and t. So x1 plus 2s plus t by 6 plus 4t equal to 0, and this is 25 over 6. Alright, so x1 is negative 2s minus 25 over 6t. Okay, we are ready to write down the basis for the null space. Basis for the null space is a solution of Ax equal to 0 basically, right? So let's write down the solution. x1, x2, x3, x4. Look, x1 is negative 2s minus 25 over 6t. x2 was our free variable, x3 is t over 6, and x4 is going to be t. Let's write it as a linear combination of s and t. Coefficient of s in the first equation is negative 2, then 1, 0, 0. Negative 25 over 6, 0, 1 by 6, 1. Alright, we got the basis for the null space. Let's write them down. Basis for the null space of A, or basis for the orthogonal complement, are going to be these two vectors, negative 2, 1, 0, 0 and negative 25 over 6, 0, 1 by 6, 1. Alright, so this is the set of basis. This is a basis for the null space, or it's a basis for the orthogonal complement of that set W. Again, it's a very simple idea. I gave you the basis for some subspace of R4, and I ask you to compute the basis for its orthogonal complement. Fairly simple deal. Assume that the given basis are the basis for the row space of A, and based on that basis for the row space, reduce matrix A into one of those echelon form, and try to figure out free variables and leading variables. Try to express leading variables in terms of free variables, and write down the basis for the null space. Alright, let me show you another way to ask a very similar type of question. Alright, so here is another way to ask a similar type of question. Let's say let W be a subspace of P2X. Remember what is P2X? P2X is a polynomial vector space consisting of polynomials of degree less than or equal to 2. Right? Suppose I give you a subspace of P2X generated by, let's say, two polynomials, x square plus 1 and 2x plus 7. Okay, what I want you to do is compute the basis, a basis for its orthogonal complement. Okay, alright. The idea again is pretty simple. Here is the solution. I'm gonna write down the basis for W. The basis for W is x square plus 1 and 2x plus 7. Remember, this can also be seen in terms of order triple, right? Ax square plus bx plus c. A is the coefficient of x square term, b is the coefficient of x power term, x to the 1 power term, and c is the constant term. This thing can be rewritten in terms of order triple 1, 0, 1, 0 to 7. Alright. So as you see now, I'm back to the previous example. In fact, this example is simpler than the previous example. Alright. Let's assume, suppose W, which is 101 and 027, forms a basis for the row space of A. Okay, I'm going to formulate this matrix A, or matrix, let's say A1, with these two rows 101, 027. Alright, try to reduce it into one of those echelon form. Realize that it's already reduced into the triangle echelon form. Have two pivots, meaning there is only one free variable, right? Let's call that free variable x3 equal to t. I'm going to write down that second equation, 2x2 plus 7x3 equal to 0, and this tells me that my x2 needs to be negative 70 over 2. I'm going to write down the first equation, x1 plus x3 equal to 0, and this tells me that x1 must be negative t. Alright, ready to write down the solution for the homogeneous system. Solution for the homogeneous system, x1, x2, x3 is going to be, negative t, negative 70 over 2, and then t. Factor t out and you will see the basis entry, negative 1, negative 7 by 2, 1. Alright. Okay, so the basis for the null space of A is going to be this particular vector, negative 1, negative 7 by 2, 1. Or you can write it in terms of polynomial. Okay, let's write it down. This is the coefficient of x square term, coefficient of x to the power 1 term, and constant term. Negative x square minus 7 over 2x plus 1. It will be wise to check if the dot product of this vector with both of them is 0 or not. Alright, let's quickly check it. Negative 1 plus 0 plus 1, that's 0, so it's orthogonal to the first vector. 0 minus 7 plus 7, that's 0 as well. Done. So this is the orthogonal complement of W. We can ask the same question, similar type of question, in a slightly different form. Alright, so maybe something like this. Find the basis for P and its orthogonal complement for this plane, 2x plus 3y minus 4z equal to 0. Any plane through origin in R3 is the subspace of R3. This is something that we have proved already earlier, right? Now let's try to find out basis for P and its orthogonal complement. I already show you how to find out vector orthogonal to this plane, all right? And that vector apparently sits in the basis. So basis for orthogonal complement of P consists of that normal vector 2, 3, negative 4. Right? This thing is done already earlier, right? So here is the solution. Okay. I assume that this is same as the basis for row space of A. Okay, my goal is to, you know, produce a matrix A and compute its null space. Okay, this is already in the triangle echelon form. That's the pivoting entry, meaning there are two free variables. Alright, let's use the parameter for them. X2 is t, x3 is s, and I'm gonna solve this x1 in terms of x2 and x3. Okay, so 2x1 plus 3t minus 4s equal to 0. I really get x1 equal to negative 3 half t plus 2s. I'm ready to write down the basis for the null space. Alright, let's do it carefully. The solution to the homogeneous system x1, x2, x3 is going to be negative 3 half t plus 2s, t and s. Write this as a linear combination of s and t. I get negative 3 half 1 0 and then 2 0 1. Alright, so the basis for the null space or basis for P, basis for the plane, is going to be all linear combination of these two vectors, negative 3 half 1 0 comma 2 0 1. Alright, again, it's perfectly fine if you write your vector in this format or that column vector format. Both are equivalent, as we mentioned earlier. Alright, if you have any question about any of this type of problem, please feel free to shoot me an email. I'll be more than happy to clarify these things with you.